it's sort of an aside. It's something that I came across a number of years ago. When I first heard about it, I was like, that's nonsense. That's clearly like, what are these people even talking about? And as I've got older, I found it more and more useful, more and more interesting. And once I started actually seeing it, I couldn't stop seeing it. So it's a thing called Conway's Law. And the basic idea of Conway's Law is that software will resemble the organization that makes it. So, okay, well, what does Conway's Law mean? So this is things like if you have one central head office, which has most of the power, and then a bunch of little satellite offices, then you'll wind up with a software system that has a central core and a whole bunch of plugins or like scripts around it or something like that. If your organization is, divided into a front end team and a back end team and a database team, then your architecture will have 3 sections of it. Yeah, in some ways it seems obvious, but then you start actually looking at bits of software and you can start seeing how that team communicated. Consequences of this for academic software development. Most academic software is built in units of either 3 BSc student months of work, 6 MSc students months of work, or 12 PhD students worth of work. And one of the other big drivers on academic software is that it has to be similar to other pieces of academic software, but not the same. It has to be similar because of the way academia is structured, because of the importance of publications. You've got to publish it somewhere. You've got to actually have people who will review it, who care about it. So you have to be reasonably similar to something other people are doing, or otherwise, where would you even publish it? But you also can't be exactly the same, because then you can't publish. Also, academic software that survives for any length of time, you have to be able to hand over to someone else. So it has to have a design that's clear enough, documentation, the social processes to do the handover, or you have to build it into your academic career. And so really what I'm saying, I guess, is that interfaces are key, because academic teams change so rapidly that yeah, you really need to think about interfaces. Anyway, this is a complete aside from what I'm actually going to talk about, but maybe it's worth thinking of or thinking about. I don't know, secret bonus for people who tuned in early, I guess. So we're now at the start. So
okay.
I'm going to wait.
So
are you chairing the session?
Yeah, I'll be chairing the session. So welcome everyone to the day 2 of the tutorial session. It's a great honor to have Martin Brain over here delivering the session. So let me quickly introduce Dr. Martin Brain. So he is a lecturer at City University College of University of London and a senior research fellow at University of Oxford. His work is broadly within the areas of automated reasoning and automated verification of software for safety and security. On the automated reasoning side, he mostly works on SAT and SMT solvers, including being the co-author of SMTLib theory of floating point and developing the CVC4 floating point theory solver. In automated verification, he mainly focuses on low-level and embedded software in C, C++, and ADA using a combination of abstract interpretation, symbolic execution, and deductive verification in tools, including Spark and CVMC/CProver. So yeah, without any loss of time, let me hand it over to Dr. Martin Bray. Martin, over to you.
Cool. Okay, so hello everyone in India. I'm Martin. Hello everyone who's watching on YouTube. And also hello everyone in the future who's watching this on YouTube, but like at some point in the future. Thank you very much for joining me. So today we've got, what, about 4 hours or something like that, which is crazy. And I'm actually going to give sort of almost 2 separate-ish but related talks. And yeah, so the first one is just going to be about what's SMT about? Where does it all fit together? What's this theory that you're modulo anyway? And into some of like, well, how would you actually use this? And so later on, we're going to try and do some hands-on things. And then afterwards, we are going to talk floating point specifically. So this is one of the particular theories, and it's one that's very, very close to my heart personally. And so hopefully we can make some sense of, well, why do we need that, and what do people do with it? Yeah, right. So Sarab is apparently going to be monitoring the chat for me, and so if you have questions, please just ask them on the chat, and then Sarab is going to like he's going to corral those and interrupt, and hopefully if you give him some really good things to ask, then hopefully we can have a bit of a conversation. I would far rather be doing this in person, because I like being able to talk to people. But yeah, so ask some really great questions, ask them in the chat, and yeah, we can have some fun as well. Cool, right, so let's get started. What's all this SMT stuff about? So the management level view of SMT solvers is that it's a box. So it's a box, and you put formula in, and you get one of 2 responses out. It's either SAT, satisfiable, i.e. there's a way that all of these formulae together can be true, or it's unsat, so there is no set of values for any of the variables, no way of putting things together that is has all of the formulae being true at the same time. So at the highest possible level, this is what we're interested in. Now, this might sound a lot like what Armin was doing yesterday, except on his slide, he has, it says SAT solver. So in that sense, the high level management view, they are very, very similar. It's a box, you feed in a formula. Where do you get formula? We'll come to that. And then you get SAT or unsat out. So Armin may have also talked about the case that really when you get a SAT answer, what you also often, but not always, often though, what you often want is a model as well. So that's an assignment of the variables in a problem to values. So, you know, it's like, okay, these formulae, they can all be true together if X is 5, Y is 7, and G is this particular array. And on the flip side, if it's unsat, if there's no way of satisfying all of those together, then you might want a proof. So I don't know how much Armin talked about sort of DRAT and proof formats for SAT solvers. SMT solvers are a bit behind in this regard because it turns out to be a much, much harder problem. But increasingly, we are seeing proof producing SMT solvers. Okay, so why is it harder? In fact, why am I not? Why is this different? Like in the management level, formula goes in a box, SAT, unsat. This is exactly what Armin's doing. The difference is in the formula, is in what language is the formula written in. So for Armin, he was talking about CNF written in Dimax format. He may well have talked a little bit about Eiger. The point is that in his case, it was propositional logic. Every variable is either true or false. It's the only values they can ever have. And all of your operations, are the Boolean ones. And really, that just kind of folds down to being CNF. So at the highest possible level, what we're really talking about today is what happens if you want to be doing SAT-like things, but your formula and your language is more expressive. Right, so why? Why on earth would we use this? People who are on the chat, there is an option to raise your hand. And I think I can do it like that. Aha. I've raised a hand. Could I just have a quick show of hands for people who have people who already make use of an SMT solver? Make use in the widest and most liberal sense of the term. Okay, so I noticed there's someone logged in as Mate Sues. Hi, Mate. Cool. Okay, so we've only actually got a handful of hands. 6. Okay, this is cool. This is cool. That's great. Okay, so perhaps later on, when we're taking a break or something, maybe you want to talk to some of these people and just be like, hey, the stuff he's saying is that how does this work out? Yeah. Okay, so some people here, they've already got their formula. Otherwise, why do we want them? Right. So what are we doing? What's useful? So one approach is that this allows us to kind of operationalize theoretical computer science. So an awful lot of theoretical computer science is you're basically taking, here's a thing in computing, how do we talk about it in maths? How do we talk about it in formulae? And a lot of that becomes a paper exercise. Okay, so here's, here's our formalization of this particular database system. These are the rules we wanted to follow. Okay. Well, if you formalize that, if those rules could be written down as a formula that you feed into an SMT solver, suddenly you have a way of checking not only the rules, do the rules make sense? Do they fit together? Do they actually work? And also, you can do this, but it then gives you a way of building a checker. So if you care about databases, then suddenly your work is not just about writing papers and doing maths about databases. Suddenly you have a route to doing this practically with real databases. That's one sort of thought, is that if you've got these kind of black box solvers, then a huge part of computing, which is let's turn it into a formula, will then give you a route to doing things practically. Theoretical computer science, therefore, at this point, is one of the things that makes theoretical computer science actually applied theoretical computer science. Is that even a thing? who knows? So another one is the use of formulae as representations of sets. So this is something that's been invented independently, I think at least 3 times in verification, because there's one time when it was invented by Tony Hoare and Floyd as well. There was another time when it was invented by King in symbolic execution, and there's another time when it was invented by, I want to credit Armin actually, but in symbolic model checking. And the idea is basically that if you want to reason about programs, what you want to do is you want to say, these are all the possible states that a program can be in. And so really that's just a set. This is the set of reachable states. This is the set of program states when I enter this function. Okay. And if you look at early work, if you look at explicit state model checking, if you look at tools like Spin, they're a lot more upfront about the fact that they're doing things with sets. They actually keep a set of, these are the reachable states in my automata. So yeah, this is a thing you want to do. There's a lot of things that you can reduce to let's reason about sets. The problem is, of course, if your sets start getting very large, at a certain point you just can't store them in the computer anymore. You know, so if you want to, you talk about the set of states at the start of this function, well, as soon as you've got a 64-bit variable in there, you're probably not going to be able to write all the states down. So independently, a bunch of different areas of software verification, hardware verification, and a bunch of other disciplines all hit on this idea of like, look, rather than actually explicitly writing down the set, why don't we just have a formula? And so every solution to that formula is a thing in the set, and everything in the set is a solution to the formula. It might seem like I'm kind of laboring the point on this one, but it's an important sort of sleight of hand that turns up in a hell of a lot, well, a lot of software verification, hardware verification, bunch of other fields. And nobody ever mentions it, right? They're just like, oh, well, these are, you know, this formula is the precondition. And what they're actually saying is, this formula is a representation of the set. Actually, the set's the thing we care about. And people don't generally articulate this. And maybe I and other people are partially to blame, because like, maybe the point is that our formula, that's what describes the set. And then the role of the SMT solver is to say, is this set empty? So if we want to intersect two sets, well, we just take the two formula and we add them together. And if you want to find out is the intersection empty, run it through the SMT solver, get out SAT, hopefully. In that case, it's not empty. If it comes back on SAT, they're empty. Those two sets that you're representing with formula are empty. Yeah. Also, at a practical level, there's a point about separation of concerns. If you're trying to architect a system, say a program verification system, close to my heart, one of the big architectural decisions you can make is separate out the generation of the formula, which is you know, I'm generating my formula because I want to represent sets, because I'm trying to turn theoretical computer science into something people can actually hands-on do. I want to separate the generation of formula from the handling and the resolution of the formula. This is an architectural divide. And if you look at tools like CBMC, so CBMC kind of predates just about the widespread availability of SMT solvers. So it has its own internal solver. Like pre-2000, a lot of verification systems were like this. But interestingly, it has that architectural divide. There's one part that's in charge of making the formula and another part that's in charge of resolving, dealing with, checking the satisfiability of the formula. And there is a hard architectural boundary between the two. So having SMT solvers allows this kind of separation of concerns. The other point is that it reduces your tooling effort. So again, kind of pre-2000 or something, if you wanted to build a program verification system, you really had to start from scratch and you would have to build everything. These days, half of your problem. So you need to still do the generation of the formula part, but the solving of it part, that you can just take off the shelf, and that's what I'm going to show you today, how to take it off the shelf and use it. So yeah, you've halved your problem. What was that I said about Conway's law at the start? And about units of software. Maybe the answer here is that this enables writing a program verification system to become something that an MSc or a PhD student can do. Anyway, it's enough about Conway's law. Right, so formal stuff. So I've talked about it from the sort of management point of view, and they're like, okay, well, why do you need one of these? Let's actually try and do some formal math. So it's still very, very early morning here, or at least for me it is. So I'm going to ask you quite a simple question to start with, and that's this one: 0 x 0 y x plus y. Okay, can we have a show of hands on our participant thing? How many people think that this formula is satisfiable, i.e. there is a way of picking x and a way of picking y such that all of these are true? If you believe that, if you think it's satisfiable, then put a hand up. If you don't think it's satisfiable, if you think that there are no possible x's and y's, there are absolutely none, no way you could pick x or y, that all of this could be true, then keep your hand down. Okay, so hand up means I know I can come up with an x and a y when all of these are true. Okay, so just give people a minute to put hands up or not. Okay, so we've got, cool. Okay, so how does this change your opinion, right? You're allowed to now move your hand around, okay? Is there a way of picking x and y such that all of these conditions are true? If you've got an x and a y where all of these conditions are true, you keep your hand up. It is early here, but it's not too early to play tricks on people. So people have given a different answer, or at least some people have given a different answer. There's a few people who've stuck with it, and I like that. But yeah, why should these answers be different? All I've done is I've just changed the notation, right? And people have a kind of like particular sort of emotional attachment to certain symbols, but really, I mean, like that's a cultural thing. It's also actually comparatively recent, like, you know, sort of the use of these kind of like pointy things and pluses and stuff. They're actually quite modern notation, and we could have just picked these instead. So what I'm saying is, if we actually want to answer this question, we need to ask, what do the symbols mean? Because if I kind of came out and said, actually, every time I write that club symbol, that means less than. And every time I write that heart symbol, that means plus. Then you'd think I had weird choices of notation, but it will mean the same thing, right? So first order logic. We do need a little formalism here. So a statement in first order logic has a signature, which is a set of predicates and a set of functions. So our predicates might be just the one predicate, and that's the club symbol, and our functions might be just the one thing, and that's the heart symbol. And so formula is made up of predicate followed by a bunch of terms. So can people actually see where I'm pointing with my mouse? I'm just kind of blithely assuming that you can. So this is one formula because it's got a predicate and two terms. And you can AND formulae together, you can negate them, you can put quantifiers, you can do all the usual first order logic type stuff. And the terms, so things that appear inside your predicate, they're either functions or variables. So in this case, what we're talking about, the less than symbol, that's our predicate. That's the thing that's either true or false. And it's been applied to two terms, a 0 and an x. And the same one, a 0 and a y. And on the bottom one, the predicate part is the angle, the less than. And it's two terms. And one of those terms is made up of a function application. Okay. So then if we want to talk about the semantics of it, you know, this is getting into the heart of like, are these two things actually different? Or is this just moving symbols around? So a signature, we've got predicates and functions. The way that we're going to define semantics of first order logic, and note this is not the only way of doing it. And there are even some people like Gerard who just object to the concept of separating out syntax and semantics. But for what we're doing, it's really important. So we've got an interpretation. So our interpretation is D, it's a domain, okay? So that is the world of things that we are talking about. And we've also got an interpretation map. So it takes, you know, our world, maybe actually we're talking about integers. Maybe our world is integers. Maybe our world is floating point, 32-bit floating point numbers. Maybe our world is pots and pans. Maybe our world is things that I can find on my desk right now. And so our interpretation map then takes our predicates and our functions and maps them into predicates and functions on that domain. So we say that a particular interpretation satisfies a formula if, when you evaluate that formula over D using that interpretation map, it's true. So what that means is that the interpretation map gives you a world to work in, and it gives you a meaning for those symbols. And then we say something is satisfiable if there is a world in which it's true. So back to our question, does this hold? Well, it depends on the interpretation of the symbols. And I'm using my club symbol and my heart symbol here, but I could just as well say the same thing about less than and plus, right? I'm just using these because otherwise people kind of get these notions, and which is exactly the trick I was playing on you earlier, that when I write a little cross symbol like that, that means plus, right? So formally, we've got our signature, which is club and heart. We've got our formula, which is implicitly, if we give a set formula, we mean anding all of them together. So we've got 1, 2, 3 predicates, all of these things are terms, and this one is a function application. So does it hold? Does it not hold? It depends on the interpretation. So if our interpretation, we pick D, the domain, to be the integers, and if we pick the interpretation of the club symbol to be less than on the integers, and we pick the heart symbol to be addition on the integers, then with respect to this particular interpretation, then I can't find an x and a y, both of which are greater than 0, and so that when you add x onto y, it's less. So in that case, it's unsat. However, if we're talking about a different interpretation, one where the domain is bit strings, say 3-bit bit strings, and our predicate is an unsigned less than. So 0 is less than 1, is less than 2, is less than 3, is less than 4, 5, 6, 7. And we pick our heart symbol to be a bit vector plus. In this case, I think it is satisfiable, because what we could do is, if we picked x and y, let's pick x as 1, 1, 1, 7. Let's pick y as 1, and they're both greater than 0. And when we add them up, it wraps round, we get 0, 0 is less than 7. So in this interpretation, specifically this one, it's SAT. Okay, so I did kind of play a trick on you earlier by not telling you what the interpretation was, not telling you what domain you were working in. But really, you all got the right answer because there are multiple right answers. It depends on the domain. Right, so that's really great in terms of, in a philosophical sense, because it allows us to apply this logic to many, many things. But in a practical sense, it's not massively useful, because when you write formula, you kind of don't entirely know what it's about. So what we really want is, we want to be able to fix the meaning of some symbols. So there are two kinds of approaches to doing this. One is a kind of syntactic approach, which is this one, option 1, and one is kind of a semantic approach. So what we can do, approach 1, axiomatic. So we say, okay, our original question here, that's not a particularly good question, because it's satisfiable in some interpretations and not others. So what we really need is, I should tell you what the axioms are. I should tell you what rules does this pointing angle follow, and what rules does this plus follow. Okay, so that's the axiomatic approach. So this is, if any of you've done a sort of fairly classical kind of Bourbaki style course in foundational mathematics or basic algebra or something, they will go, right, a group is anything that meets these axioms. It must be associative, it must have an identity, it must be commutative. Not commutative, inverse. Still morning here. So that's one approach. And now, from a practical point of view, the axiomatic approach, it's good because it's easy to implement. Everything you ever need to care about is in that syntax of that logic. If someone doesn't put it in as an axiom, that's fine. You know, so you just, like, your parsing becomes really simple, your representation becomes really simple, and it's also really nice and flexible. Anything people can describe, first order logic, yeah, you can do. Downsides. All of your formulae are quantified, and often very, very quantified. You need, practically, if you want to get stuff done, you need tons of axioms, and often they are not simple. So if you look at the literature on automated reasoning, this is the approach that the sort of first order provers traditionally use, is that if you want to talk about arithmetic, right, you must give me the axioms that you want your arithmetic to follow. And so if you look at tools like E and SPAS, Vampire in its classic sense, they are very much, they follow this line of things. We are first order logic, you must say your things in first order logic, and then, you know, if we produce proof, then it is true for every possible interpretation. It doesn't matter whether the interpretation is bit vector strings, it doesn't matter whether it's integers, it doesn't matter whether it's objects on Martin's desk, it's true. That's one view. So the other approach is the semantic approach, which is where we say, well, actually, really what we want is we want to fix some or all of the interpretation. So this is, I feel, kind of morally equivalent to what I should have done when I posed my first question. You know, at that point I should have gone, we're working in the integers, and those symbols are the ones you think they are. Alternatively, I should have gone, this is bit vector arithmetic. Get your bit vector hats on. So this second approach, the sort of algebraic approach, we pin down what interpretations we're talking about. We say, when you're writing those formulae, you are talking about the world of integers, and specifically the world where that club symbol means less than on the integers, and that plus symbol, that heart, is addition on the integers. All right. So why might we want to do that? Well, advantages, we can specialize our decision procedures. If you take the axiomatic view, then everything is just formulae. Really, everything is just formulae. Like, it's all first order logic. The fact that this symbol is called plus, that doesn't matter. It's just symbols. Whereas in this, the algebraic approach, we go, no, look, we know that these things are integers. We know that that is integer addition. So we can, you know, we could try out different integers. We know that 3, the symbol 3, and the heart, and 5, we know that we can actually simplify that to 8. So that allows us to write really fast decision procedures. It also allows us to build counterexamples, which is what I did here. I gave you specific concrete values. I said, look, try X is 111, Y is 001. And I could do that because I knew what interpretation we're working with. So we get counterexamples. It also makes our formulae overall simple because we're just like, okay, look, this is integers. It's just integers. I don't need to define what the integers are. You know what the integers are. I know what the integers are. Everyone knows. It's simple. However, there is a flip side. There is a disadvantage of doing things this way, which is that the solver has to have some knowledge of what the integers are. The solver has to, somewhere buried in the code of the solver has to be a thing saying, okay, right. And when they write that symbol, it means integer plus, and let's specialize to things we can do with integer plus. And what that means is that, unlike the axiomatic approach, where if they suddenly just want to start, okay, let's talk about complex numbers. Sure, right, we'll write down some axioms for the complex numbers, and then you're fine, you're good to go. And they can just change it in the input. If you take this approach, the sort of model theoretic approach, then you suddenly want to reason about complex numbers. Okay, right, well, first you're going to need, you need to be able to modify your solver. You're going to need someone who can come up with a smart decision procedure about complex numbers. Once you've kind of written the paper on how to do that, then you are actually have to implement it within your solver. You know, like in the axiomatic approach, you know, you just look up a suitable set of axioms and just use them. Here, you've probably got 6 months of work ahead of you. Best case, maybe years. So the two different approaches, the axiomatic one is very, very flexible, but because the solver inherently doesn't know what it's talking about, it just knows symbols, it limits what you can do. Once you know, once you've fixed the meaning of the symbols, then you can do a lot more. But that requires you to actually have done the work. Satisfiability modulo theories is the field that follows the second approach. I mean, really, the name in some ways is kind of badly chosen. We should be satisfiability modulo interpretations, because really that's actually what we're doing. But the point is that back right at our first slide, the management view, we're different to what Armin's doing because our formulae are first order logic. But the really critical thing is the first order logic with respect to particular interpretations, with respect to particular things, so that we can say this is first order logic, but we also have things for talking about bit vectors. And when you say that this variable is a bit vector of length 7 bits, and we're going to add it up to some others, then we know exactly what that means. And that can be built into the solver, which is great, as long as the theory you want is already built into the solver. But it turns out that overall as a field, we've made quite a lot of progress, and mostly it is. So at this point, I think I'm going to have a quick pause. I think everybody else should have a quick pause as well, because we've been talking for about 3/4 of an hour. So last time I did this in person, this is the point where I said to everyone, could you stand up? And if you're at home and if you have space to, please do actually stand up. I'm going to in a minute. I just actually, why don't I do it? Right, okay. So you can stand up and just have a little bit of a shake around and a move around. Because otherwise we're just sitting and it's easy, you know, it's an intense day, it's Saturday. So, and you stand up, but also can you do one other thing? I'm gonna have a break for a few minutes. Can you get on Discord, right? So this is specifically for everyone actually at the school. I'm really sorry, everyone on YouTube, and in the future you can't do this. Well, maybe you can, but can you get on Discord? And can you just post in the main channel, which Sarah is very helpfully going to write in the chat for me, which channel he wants all of this to go into. You post on that main channel just a quick message saying hi, who you are, what you're working on, and one thing that you think is really cool. And it can be something from summer school, it can be something from computer science in general. If you don't think any of that's cool at all, it can just be something, just anything, right? So who you are, what you're working on, something you think's cool, and it should go in #general. Okay, so you've got like about 5 minutes to stand up, have a shake, move around, and just post that to general. Okay, so please do that, and then we'll start again in a minute.
What was the third question?
So the third one was something you think's cool. So
Okay.
okay, so I've posted to general. Come on, we've only got a few minutes. Get typing. It says several people are typing. Is that everyone? Cool. So the first person to post, I should point out, is Dennis. He has free online a really fun book of here are a load of problems, here are a load of applications, and here's how to turn them into things in SAT and things in SMT. So that's the kind of thing I was talking about when I said about formalization and making theoretical computer science into something you can really do. He's got a whole book on this. You should have a look at it. It's really good. Like, the next person, the person I name checked earlier, is actually one of the developers, one of the solvers, like both one of the SAT solvers, really, really good SAT solver, and also works on one of the SMT solvers. So that's why he specifically got name checked. But yeah, people are posting. Okay, this is great. Like, so we're coming up to the end of the break. If you haven't stood up, how to walk around, please do so. I'm going to. Right. I'll leave people to type, and everyone else who's jumping up and down or moving around, this kind of thing. That's great. I'm gonna make a quick start. Right, so SMTLib. So what I've talked about so far is this idea of SMT in general, satisfiability modulate theories. Really should be satisfiability modulate interpretations. That's the general concept. Then you'll hear people talk about SMTLib. So SMTLib is a particular initiative, and to me, it's one of the things that makes this field just awesome to work on. Okay, so we are incredibly lucky. Like I've worked in a number of other like fields and areas of computing, and like SMT is so blessed in this regard. It's amazing. Very early on in the development of the field, a number of people realized that there was benefit to making all of the solvers able to interoperate. And that way we could share benchmarks, we can actually meaningfully compare different solvers. And that's sort of the origin of the SMTLib initiative. So the idea was, let's have a standard. Let's have a standard that not only standardizes the syntax of how you write down formulae, but also the semantics. And we need to standardize the semantics because that is the fixing the interpretation part that I was banging on about earlier. So this is what SMTLib's about. It's about having a standardized language. And at the moment that includes interpretations for arithmetic, both integer and reals, arrays, and you can have arrays made up of anything. So you could have array, normally it's arrays indexed by integers, containing integers, but it doesn't have to be. You've got bit vectors. So when I was talking about bit vector arithmetic, that's all formalized, that's built into most of the solvers. You've got floating point, which is what we're going to be talking about after the break in a bit. You've also now got a theory of strings and regular expressions. So if you want to do stuff with, particularly a lot of web code and a lot of validating inputs, really that's a find a magic string that goes through this set of inputs. Data types as well, which allow you to do kind of lists, trees, that sort of thing. One thing I should say about SMTLib is that the format is intended to be machine readable and to prioritize machine readability over human readability. And that means like to write it as human is sometimes a bit kind of tedious, but it does make it easier for solver developers. And this is really an initiative about and by the people who build solvers. SMTLib also has a benchmark library, which is now into the hundreds of thousands of benchmarks. I don't know exactly how big it is. I'm not sure if we've passed 500,000 yet, but it's heading that way. There is also associated with SMTLib SMT Comp, which is a competition which is held annually. Competition. It's a chance to demo that all of our solvers actually work and try and replicate some of the experimental work. It improves the quality of experimental work we do as a field. But I thought rather than just like talk you through what's in SMTLib, why don't I tell you about the website, because it's all there, and in practice, it's the website that you're going to use. So what I'm going to try and do, let's see if this works, is I'm going to stop sharing that screen. Maybe that's worked. And now I'm just huge, which is not great, but you know, so so I'm kind of hoping you might be able to see my web browser now. Can someone shout if you can't see my web browser now?
We can see your browser.
Excellent, excellent. Okay, so this is the SMTLib website. It's smt-lib.org, but it forwards through to this URL. So things are, can everyone read the text as well? I don't know how well the text compresses. But.
Maybe if you increase the font size a little bit, might help.
How's that?
Yeah, this is definitely okay.
Okay, so on the sidebar, if we click on language, then we get ourselves this, which is this here is the SMTLib standard. It's also kind of a boast. It's now up to 104 pages. So I would not recommend this as the way to start learning SMTLib. So just thinking, so it has sort of basic assumptions, which is talking about what SMT is, syntax, semantics. There's an awful lot in here. There's a new version in the works, SMTLib 3, which should hopefully be out within a year or two. The standard doesn't move very quickly for deliberate reasons because interfaces are important. That's why I was talking about Conway's law. So that's really the definitive reference. If you need to understand how does this work, what can I assume, what exactly does this do, that's where it'll be. More interestingly though, we have this thing saying theories. So SMTLib has a distinction which confuses a lot of people to start with between theories and logics. So a theory is effectively, it's the fixing of the interpretation of some symbol. So it gives us a signature. So it says, okay, you can use plus as a symbol, you can use less than as a symbol. And it also then gives what semantics are. So each of these documents gives us one of these theories, one of these fixed interpretations. So let's have reals and ints. So another common mistake, and one I made back when I was first doing this, is looking at these theory files and that they're in structured format and assuming that you fed the theory file into the solver. Where do you put the theory file? This is not right. So this is what I was saying about that first approach. That's the axiomatic approach, where you'd feed in a series of axioms that describe the interpretations you want to work on. SMT does not work like that. These theory files are the specification for what the solver should do. So if you read these, you will understand, okay, this is what, if you have a theory that is of reals and ints, this is what it is. And it says we have sorts, we have integers, they don't take any arguments. We have reals, they don't take any arguments. We have a bunch of functions. There's subtract, plus, multiply, divide. We have a less than symbol, which takes an int and an int and gives you a Boolean. We also have a similar thing, less than, for reals. And it takes two reals and it gives you a Boolean. So anything that's giving a Boolean is effectively a predicate in the terms I was talking about earlier. Anything that's going from one thing in the domain of interpretation to another is a function. Cool. So those are our current standard theories. There are a few more that are under development, but if you want to know, okay, what can I do with strings in an SMT solver? That's the file you want to look at. This one here. Then there's the concept of logics. So if we click on logics. So this is kind of a bit of an alphabet soup. So this is one of the things that confuses a lot of people when they first look at SMT. They find these kind of crazy strings of letters. Like, what on earth does this mean when you're saying you're working in this logic? Okay, so the cheat sheet is here, right? This is the cheat sheet. So what a logic is it combines one or more theories and some extra restrictions. So anything that says QF means that you don't have any universal quantifiers. You can't say this is true for every integer. A's and AX are for arrays, BV for bit vector, FP, we should remove the forthcoming because it's been standardized for years now. Integer, arithmetic, real. So if I pick one of these, you know, this is quantifier free, arrays, uninterpreted functions, and linear arithmetic. This one allows quantifiers, it's arrays, uninterpreted functions, non-linear, integer, and real arithmetic. So from the string, excuse me, from the string you can figure out what theories are supported, and so what will the solver's working on. So you might have mixed problems, you might have things that are bit vectors and arrays, that's a really common, popular one. You might have, okay, well, this is actually just reals and floating point. It's not listed on there, but it does exist. So the reason that you need a kind of set logic, the reason we have these kind of logic things, is to help separate out the different capabilities of different solvers. So to be an SMT solver, you do not have to implement all of the theories. In fact, it's relatively rare to find solvers that implement all of the theories. I think there are two solvers that implement all of the standard theories. Most people choose to specialize. Most people implement one or maybe two theories. And so these strings, you know, if you have only implemented linear arithmetic, well, if you get that, you know it's nonlinear integer arithmetic, you know you can't handle it. So the theory fixes the signature, it fixes what operations you've got to play with, effectively what data types you've got to play with. The logic then tells you which of the theories you've got access to. And each one has a file that describes what's actually allowed. So closed quantifier free formula built over fixed size bit vectors, that'll be the theory, and arrays with extension, but with the additional restriction that all of the array terms are the form bit vector to bit vector. That's QFABV. It's a popular one. So that's the difference between theories and logics. So the thing that is really, really useful here, the examples. So if you generally want to know, okay, how do I write something in SMTLib? Just look at the examples. It's really the easiest way of learning, maybe apart from the thing that we're about to do. But, so overall, it's S expressions, so it's Lisp-like, and the general pattern is that you have commands, and so you've got a bunch of commands. First one is just setting an option, which is saying like you don't have to tell us when a command succeeds. Then you've got your set logic. So that's then the logic string I was talking about, in this case, quantify free uninterpreted functions. So that means then solver can at that point go, hey, I don't support that, sorry. Or you can filter down and just be like, okay, we're only going to do this particular logic, this combination, this logic which combines these particular theories. So this is a little bit misleading. It declares a const. This is a constant in the sense that it is a function that takes no arguments. So remember when I was talking about signature, we talked about functions. So okay, you've got to fix your functions. So in a sense, variables, this is creating a P that is a variable. And it's saying this is Boolean. We assert that particular formula is true. And then we call check set, and that tells us whether it's satisfiable or not. And we're done. That's it. That's how you use an SMT solver. That's the simplest way. And there are examples here, linear arithmetic, getting values back. So this is where I say you not only get SAT or unsat, but if you set the option to produce models, then when you get SAT back, you can also call command get model, and it will tell you what model, what values the variables have to make things satisfiable. And there's a load more here, and you can have a look at these.
So Martin, there is a question.
Cool.
So the question states that how do these theories relate with each other in terms of theoretical solving complexity? So the question states that suppose a problem can be encoded in IDL as well as LIA. which logic one should go for, and what are the different trade-off of doing that?
You should probably go for the most minimal logic you can, the most minimal one you need. In the specific case, the difference logics, I'm not aware of people doing much with them, so I don't know how much difference it will make. But yeah, different logics do have different complexities. Overall, go with the most minimal one. The uses the least. That's your best bet. I think a more detailed answer than that might take me a bit longer. I'm happy to discuss it over chat though, if you want. Is that okay?
Yeah, so Ravi, is there any follow-up question, or is this okay? Yeah, I think yeah, he's it's
Cool. Okay.
seems to be satisfied. Yeah.
Excellent. That's good. So I guess the last thing I want to show you on here is the benchmark link. So this links to all of the GitLab repositories where the benchmarks are kept, and they're sorted by logic. So say you wanted to care about, I think somebody just asked me a question about linear arithmetic. Okay, let's find out what benchmarks we've already got for it. So you click on this, it takes us through to the Git repository. And within that, we'll see that there are a whole bunch of directories. I wonder what this one is. Prime. And this contains just a bunch of SMT2 files. So if you're developing a solver, you've got standard things to benchmark against. If you're developing a tool, then if you contribute to this repository, then people will target solvers towards them. So here we've got a bunch of functions. Some are asserted to be in particular ranges, and then we've got these crazy big assertions at the end, and a checkset and an exit. Cool. So I think that's pretty much everything I wanted to say about SMTLib. Let me just have a look at my slides. Just seeing where we go next. That is if Zoom will let me. Well, okay, so yeah, let's talk a little bit about this. So okay, I'm not quite sure what it thinks it's sharing at the moment. Can you see some slides? Maybe you can?
Yes, we can.
Yes.
Excellent, excellent. And they're still saying about SMTLib.
Yes.
Cool. Right, so solvers. Let's talk a little bit about solvers. So there are many to choose from. So this is actually a screenshot of Wikipedia, which shows you what kind of quality scientist I am. But like, you know, it's got to the stage where there's even a Wikipedia list of SMT solvers. So here, I'm not going to go through all of them, but, you know, got CVC4, one of the solvers I work on. We've got just cut off at the bottom STP. Mate is here. We have Bulecta. So this is a solver that Armin started. I think he wrote the very first version of it, but these days it's Einar and Matthias who run it. I don't know, do we have any of the other solver authors here? Silence. If there are, post in general, and I'm sure people will say hey. So you got so many of these things. Well, how do you pick? So this question has been asked often enough that I now have a stock tweet about it. So the answer is try all of the different solvers you can. So the whole point of SMTLib is to try and make these solvers interoperable, so that what works on one should work on the other. Normally there's a small amount of glue and fixing around it, but seriously, if you can work with multiple solvers, there are always going to be cases where this one solves it better than that one, but then you change the problem slightly and it shifts back the other way. Also, from a user and application point of view, what the best solver is will change over time. See what I was saying about Conway's law and interfaces and handover. So yeah, what you really want to do is try and get experience using a number of different solvers. And as luck would have it, that's actually really easy now. So in terms of, there are two solvers I know of which have web interfaces. So if, as I will do in a minute, we go to this URL, it's a web interface, you can run CVC4. There's another one, it's a web interface, you can run Z3. Local installs, almost all of the main SMT solvers are open source. Even the ones that aren't are generally available as binary, free to use for academia. They're not difficult to install. Mostly it's just here is the executable, you could run it. The other things I should plug, so these, if you just run the binary by itself, that's using the text input. I would, any project you're working on, if possible, I would start using the text input. Because that way it's a lot easier to debug. If you've got an option for text input, you can generate things to go in the SMTLib library, which is always really appreciated by solver authors, and also means people optimize solvers for your problem. So it's win-win. But increasingly, people are also like, okay, well, we don't just want to use the text, and so there are two kinds of integration that are getting popular. So either via Python, and there's a library called PySMT, which allows you, so most solvers have their own kind of API as well. But the advantage of PySMT is that you can keep the API the same, but you can switch which solver you're using. So that then means that at very low development effort, you just use this library and you can then just swap out which solver you want. So when you get to doing results, okay, well, switch, run one, and you can then just pick which solver's best, and you can put the whole results table in your paper, like we've compared different solvers, and it's pretty much trivial to do. See what I was saying about interfaces and Conway's law. Also, there is a relatively new library called SMT Switch, which is a C++ library that does the same thing. Now, this, certainly the CVC4 team have committed to trying to support this long term. and keep it up to date and keep it working with different solvers. So the idea here is C API, you can just build expressions like that and just call a solver. It just works, and then you can easily switch out which solver you use. So because I'm a little bit shorter of time than I wanted, what I'm going to do is I'm going to leave these exercises as a challenge for you. So we're about to go to a break, so I'll make sure these slides get sent, so they put them up on the web. But let me just show you the web interface. So that is if I can swap sharing quickly. And no, that's Unix. Okay, so this is the web interface to CVC4. So we've got a program here, an SAT formula really. And what it does, it says set logic. So this is quantify 3-bit vectors. We've got x1, x2, x1, and x0, all 3-bit vectors. We've got 2 booleans, and we've got this horrific mess of divides, 2 assertions and a check SAT. And if we press run, at the bottom, we get SAT. Cool. Okay, it's kind of that straightforward. And if I click here, we've got a language, SMT2, and somewhere, if I can find it in the UI, we have a menu of examples. So arithmetic, quantify 3 nonlinear real arithmetic, 2 variables, bunch of assertions, check SAT, load. What do we want? Got separation. So CVC4 now has a theory for dealing with separation logic. Something relatively simple. So this is an array benchmark. So you've got a bunch of examples there. You can use them interactively. You can play. You can just press go. All right, it's that simple to get into. If only Zoom was this cooperative. And cool. So that's some exercises for you to try out. Project ideas. There are loads and loads of cool things you can do here. So one obvious thing, if you are building any kind of sort of theoretical computer science tool, if you're generating formula at some point, try integrating an SMT solver. It's good practice, it's really straightforward, and it suddenly gives you this extra capability that you can focus on that architectural divide. You can focus on generating the formula without having to think about what you do with the formula. SMTLib always needs more interesting, challenging problems. Some of the logics are quite heavily used and so have a lot of challenge problems. Other logics aren't as popular, aren't as commonly used, and so we don't get that many more benchmarks in. There is a feedback loop here. If you have a logic that you care about, if you have a logic that's important to your application, please submit some benchmarks. The more benchmarks get submitted, the more important that will be, and the more people will work on it. So it's really worth it. Another approach, another thing you can do, we haven't actually talked yet about how decision procedures work, but that's a great area to get into. And coming up with new decision procedures for existing theories it's a really interesting challenge, and it's, having done it this number of times, like it's really great because it's one of these areas where the difference between the chain from I've got a great idea, I've done the maths, and I've implemented it and got the results, that's actually really short. Like in lots of areas of computer science, that's like years. In SMT, you can often get that down to weeks or months. To go from scratch to a new decision procedure, you can just take the solvers off the shelf, and many of them are very straightforward to modify. So yeah, this is a project idea. I'm always happy to talk to people about that. Entirely new theories. Again, what I was saying earlier about you have to build the theory, the understanding of the theory into the solver. So that means that we're limited to just the theories that we have at the moment. There are a bunch of extra non-standard theories. So theories of sets, theories of multisets, theories of tables for SQL-like things, fixed point arithmetic, separation logic. These are all sort of there are solvers that do have them, but that's not the whole world. There are still exciting new theories to be had. Maybe something to do with graphs, being able to search over the space of non-isomorphic graphs. There's one paper on doing that that's really good, but it's not had a follow-up, so there's scope there. Also, writing your own solver. This is not as hard as people think. It's not easy, but it's not actually insanely difficult either. You've got the syntax, you've got the semantics, you've got a very large set of test cases. Writing a competitive solver that supports all of the theories is a big task, but writing a special purpose solver that supports one theory and does something interesting with that is not actually a huge amount of work. So it's a thought. Right, so conclusions. At the management level, SMT is formula in, SAT or unsat, potentially a model or a proof out. The really key thing that differentiates us from what Armin's doing is that this is first order, so that we have functions, we have variables over things other than just true and false. And we have the thing that differentiates us from just being a general first order prover is that we fix the meaning of some of the symbols. So we're making sure that symbol is a plus, and we're making sure that that symbol is a less than, and that they are on bit vectors or they are on integers. The SMTLib language standard gives us interoperability. It gives us common benchmark suites. It gives us extensive regression test suites. Until you work, and until you work with this, you may not appreciate the value of this. It is incredibly valuable as a field. Like, I don't want to say we're unique in that, but it makes life so much easier, allows people to be way more productive. Yeah. Also, Conway's Law. Think about it. Right. So thank you very much for your time and attention. I think if I've got my timings right, we've got a half-hour break now, and then when we come back, we will be talking about a specific theory, which is one very close to my heart, which is the theory of floating point. And we're going to be doing that, I think, in 2 parts with a mingle break in the middle. Is that right, Sarah?
So I think 15 minutes break is scheduled right now, but if you want to adjust, we can do that. So 15 minutes break, and then at 4 o'clock there is a half an hour break. And
Okay.
meanwhile, yeah, during that time, people are free to hang out on the Discord breakout rooms.
Cool. Okay. 15-minute break then. Get up, walk around, do stuff. I'm certainly going to, and then we'll be ready to talk floating point. Cool.
Okay. Yeah. So so everyone, please reconvene. We'll start at 15:15 Indian Standard Time.
Cool. Okay.